We're back in the Art of Electronics, that is, Learning the Art of Electronics Hands-On Lab Course book by Thomas Hayes. And we're moving into a slightly new area here where we're going to consider the effects of positive feedback. But in order to understand a little of that, the author is using an example of the situation where you want to compare two signals and provide a switch when the comparison is when the two signals are the same and a different signal when they are different. Or another way to put it is when one input is positive relative to the other, you want one output. And when that same input is negative with respect to the other, you want a negative output. So what is shown in this picture is a comparison between an op-amp and a specific device made for that purpose called a comparator. Where we're going to go eventually is to show how we can use positive feedback with a comparator to improve its performance. But we're going to start out by answering the question, why don't we just use a regular op-amp? The sine wave that you see here is the input, and the two signals, and it may be hard to see, but there are actually two signals here. One is right there, and one is just a little bit to the left of it there. The slower one, that is the one that takes longer to get to zero and takes longer to get to the positive, is the op-amp. The faster one is the comparator. Now the specific comparator that the author suggests is the LM311. We've been using the LF411 and some other op-amps, and so I used an LF411 here, which is what this was originally done from. So let's take a look at the output of the waveform software using the analog discovery. And first, let me show you the circuit itself. It's over here, and this is the LM311, the comparator. This is an LF411, which is a standard operational amplifier. They're wired up in accordance with this schematic. That is, waveform 1, the waveform generator, or number 1 from the analog discovery, is connected to the input of this LF411, and it's also connected to this input of the LM311. It happens these are I didn't draw it in here, but these are the positive or non-inverting input to the amplifier and the positive input to the comparator. The negative inputs, or in the case of the op-amp, the inverting input, is connected to ground in both cases. I'm using the plus and minus 5 volt supplies from the analog discovery to power both circuits, and I caution you, be careful. Even though these are two identical looking ICs, for example, 5 volts on the LM311 is on pin 8, whereas the LF411, it's on pin 7. Pin 4 is still the minus 5 volt supply, so you may get confused. Be careful, you always read the spec sheet and carefully look at the pinout. Another difference with the comparator is it has an open collector. In fact, it has an open collector and an open emitter on its output. The open collector requires a pull-up resistor Otherwise, the output will take forever to get to a higher voltage, because if you have a high input impedance from the next stage down, that high input impedance is what has to drive this transistor, and it will really slow down the output. So you always want to use a pull-up resistor. In this case, I'm using a 1K pull-up resistor to plus 5 volts. And then the collector is connected to ground. I'll refer you to the LM311 spec sheet if you want to see a little more about that. So now let's take a look at the Analog Discovery's waveform software. So at the top, that is the yellow trace, channel 1, is connected to the output of the amplifier, of the operational amplifier. And you may notice that it swings from plus 5 to minus 5 volts because it's being supplied off a dual supply. I'll show you the 0 point right there. So this is 4 volts. The top is a little above 4 volts, and the bottom is close to minus 4 volts. On the bottom is the output of the comparator. And you may notice, I'll turn this on, if you look over here on the left, I realize you probably can't see that yet. You may see that this point is at 0 volts and this point is at 5 volts. And one of the nice things about the comparator is it does drive a little bit closer to the plus 5 volt supply with that pull-up resistor. But I want you to especially pay attention to the point of transition here. So let me focus on that. And now what we're going to do is change the time base from 200 millivolts or milliseconds per division to 50 microseconds per division. You may notice that the op amp is starting to get slow, and the comparator looks like it might be doing something a little funny on its transition. So let's go ahead and go to 10 microseconds per division. Now you see that the op amp is incredibly slow and the comparator is oscillating. This is common with a comparator without the proper circuitry around it. The idea of a comparator is to produce a very fast transition, but it is not frequency compensated. As a result, as the author points out, you can get oscillations in a comparator that you wouldn't get ordinarily in an operational amplifier. Let's go down to 1 microsecond per division, and we will slide everything over a little bit so that you can see what is happening to the comparator. It's going through what looks to me like about 6 cycles. And part of the reason is that what we are feeding it is a sine wave, and a sine wave has a very slow transition. So there is a part of its input curve where the comparator is operating as an analog amplifier, a pretty high gain analog amplifier, and a pretty high frequency analog amplifier. So we're getting oscillation. We're going to try to solve that using positive feedback, which we haven't seen so far, except if you've been watching my videos for some time, you know I did some on oscillators some time ago, including one on the Colpitts oscillator and the conditions for stability and so on. But in this series, we haven't talked about positive feedback so far, but that's what we're going to talk about next. The author compares 3 different circuit configurations. Maybe I'm using the word compare too much. Offers, let's say, 3 different circuit configurations. and points out that the problem with 100% positive feedback is this comparator will simply lock up at one of the supply rails. In other words, it'll either go all the way high or all the way low, and it pretty much will stay there. You have to really drive this input with the voltage slightly above the supply rails to get it to switch from that condition. So it's pretty much useless. On the other hand, this configuration, which is what we had to begin with, is an open loop configuration, and as we saw, it tends to oscillate and cause all sorts of problems. So what he suggests is this kind of thing, where we use a voltage divider to provide a portion of the output as positive feedback. So that is what is shown in this circuit, and this is what I have implemented, but I have made a few changes. I changed this resistor to a 2.2K because I'm only using 5 volts. I changed this resistor to a 220K instead of a 300K because I found that I got a little more stable results by doing that. But the basic idea is the same. It'll work with 300, but it's right on the edge of oscillation, at least with a 1 kilohertz sine wave. So I put in a 220, and it seems to be pretty stable. So let's take a look at that. Here is the same display. In other words, this is the op amp, and you see it's a very slow response. This is the comparator. Notice that it switches long before the output of the op amp begins to approach even the mid-range. I'm triggering on right about here of the op amp, and you'll notice that there is still a little bit of instability because remember we're using a sine wave here, so it has a slow rate of change. If we go to a square wave, you notice that it sharpens up considerably. Both sharpen up. And the reason is that there is the input wave spends very little of its time in the transition region. In other words, it snaps from one point to the other. Let's go back now to a sine wave, but let's go to a higher frequency, like say 10 kilohertz. There you see, because the frequency is much faster, both the comparator output and the op amp output begin to react a little quicker, but that's only because of the input wave. Using a 1 kilohertz sine wave, I found that about a 220K feedback resistor with a 1K input resistor to ground on the positive or non-inverting input was about right. So, what is the basic idea of this? Well, it is that a comparator provides much faster switching than an op amp. If you're trying to detect when a signal changes from, say, a negative value to a positive value, or say from ground to positive, or the reverse, you're much better off using a comparator than an op amp. And with a comparator, you can actually get even better results if you incorporate a little hysteresis in the circuit. And hysteresis, all that means is that the circuit actually contains a hesitancy, if you will. The positive feedback using the voltage divider causes the comparator, when it begins to switch a little bit, to switch all the way, and eliminates all of that oscillation that we saw early on. So once again, I hope this has been an instructive video. I'm enjoying working with this Art of Electronics lab manual, and I hope you're enjoying the videos. even more, I hope that you are getting a copy of your own book, or at least if you don't do that, at least trying some of these experiments in the lab. Once again, I look forward to some more videos, and in the meantime, have a nice day.